Chapter 5, Exponential and Logarithmic Functions. Section 1, we're going to be looking at exponential functions and their graphs, just to familiarize ourselves a little bit. Exponential functions. So far, this text has dealt mainly with algebraic functions, which includes polynomial functions and rational functions. So in this chapter, we're going to study two types of non-algebraic functions, specifically exponential and logarithmic functions. These functions are examples of transcendental functions, and so you can see that the definition of exponential function is the exponential function f with base a is denoted by f of x equal to a to the x. And so when we're talking about this is our base, and then this is our exponent, just to make sure you know what we're talking about when we say base. Where a is greater than 0, a doesn't equal 1, and x is any real number. The base a equals 1 is excluded because 1 to any power is just 1. And so you can see that here, 1 to x is just equal to 1. This is a constant function and not an exponential function. So that's why we had to say that a can't equal 1. We have evaluated a to the x for integer and rational values of x. So for example, you know that 4/3 is 64. And 4 to the 1/2, which we could also say is square root of 4, is 2. However, to evaluate 4 to the x for any real number x, you need to interpret forms with irrational exponents. So let's first get familiar with our calculator. Now for this chapter, you do need to make sure that you're using a scientific calculator, not a simple calculator. So let's first become familiar with it and make sure we know how to evaluate functions just by plugging in values. So say we have this function f of x equals 2 to the x, and we have the x value of negative 3.1. So in your calculator, you need to figure out which button it's going to be. And a lot of times they'll have like an x to the y power or something. And so you want to see, how do you get 2 to the negative 3.1? In some calculators, you'll hit the 2, and then you might use a button like a housetop button, and then you would type in negative 3.1. Make sure you also know where your negative button is on that calculator as well. Type that in and see what you get. And we'll come back into that. The other one is 2 to the negative x. So if we're typing that one in, we would want 2, and we're going to be plugging pi in this time. So 2, and you would, on my calculator, use the little housetop button here, and then negative pi. And so a lot of times you have to put this part in parentheses as well. So we can see what 2 to the negative pi might look like. And then 0.6 to the x. Well, we want to pick x to be 3/2, so we're going to have to put, let's see, 0.6, and I would have to use my housetop button here. And then my x value is going to be 3/2, so I would need to put that in parentheses, because otherwise it'll just do the 3 and then divide the whole thing by 1/2. So again, make sure you use parentheses when you're plugging that 3/2 in. So 0.6 to the 3/2. So I want you to kind of type those in, pause the video if you need to, and see what values you get, and then let's compare. So you can see here that f of negative 3.1, remember that's just instructions. This is just instructions. And so 2 to the negative 3.1, we talked about how that was 2. And in our case, housetop button, negative 3.1. You should have gotten 0.1166291. Now, if you're doing anything for me, I always like 3 decimal places. So in this case, we would have to say 0.117. Make sure you read your instructions. So on your homework, it may say 2 decimal places or 3 decimal places. Just make sure you read your instructions. But for calculator purposes, let's make sure we're getting the same display here. And so 2 to the negative pi. So we would say 2 housetop negative, and you should have a pi button. Always use your pi button. Don't use 3.14. Don't use 22/7. Use your pi button. And you should get point round to 3 decimals, 113. And the last one, 0.6 to 3/2. You should get 0.465. And yes, I will take off a rounding, because 0.464, this shows me that you don't know how to round appropriately. And we have not taught rounding in this course. And so that's an assumed skill. So make sure you know 0.465. These exponentials being said, let's look at what their graphs would look like. So in the same coordinate plane, we're going to sketch the graph of each of these functions. So we're going to look at y equals 2 to the x and y equals 4 to the x. So you can see here the table below lists some values for each of the function, and it shows the graphs of the two functions. So here's how I would kind of figure out what do these graphs look like. So these are my equations, and I would plug in -3. Now how do I get 1/8? Well, that's because 2 to the -3, remember your rules of exponents, that's really the same as 1/2 cubed. And so that's how we got the 1/8. Same thing with 1/4. That'd be 2 to the -2, which is 1/2 squared, which is 1/4. 2 to the -1, that would be 1/2 to the first, which is just 1/2. 2 to the 0, anything to 0 powers 1. 2 to the first gives me 2, and 2 squared gives me 4. Then below this, let's check this out. So if I do 4 to the -3, same as above, that'd be 1/4 cubed, so we got 1/64. 4 to the -2, you bring that down below, and it gives you 1/4 squared, which is 1/16. 4 to the -1 is 1/4. 4 to the 0, anything to 0 powers 1. 4 to the first, 4 squared, etc. So if you go in here and look at this, you can see that at the 1, we got the same value. And so you can see that here, that they both have this point. And that's pretty true for a lot of your exponentials, because anything to 0 power is just 1. You can see that although we were getting smaller and smaller as we came here to the left, we're just kind of floating above this x-axis because we're just getting smaller and smaller fractions. But we are not getting a 0 value. Then the larger the base, the quicker it got large. You can see that just looking at base 4 versus base 2, we got up to 16. So kind of the larger the base, the sharper this curve is going to be. So note that both graphs are increasing. More of the graph of 4 to the x is increasing more rapidly, as I just stated, than the graph of 2 to the x. So the basic characteristics of exponential functions, and this is what I would write down. The basic characteristics of exponential functions y equal a to the x are summarized here. So the graph of y equals a to the x, the domain is -infinity to +infinity, and the range is 0 to infinity. The y-intercept is 0, 1. It's always increasing, well, just in the case of y equals a to the x, and the x-axis is a horizontal asymptote. As a to the x approaches 0, x approaches -infinity. And it's also continuous. And there we just sketched this little graph over here to the side in your notes. Now that we have an idea of what these graphs kind of look like, we're going to look at the natural base e. In many applications, the most convenient choice for a base is the irrational number e. And so if you go in your calculator and you type in the e button, it'll probably give you like a little house top expecting some exponent. So just put a 1 there, and you should get this number, 2.7182188828. Okay? That being said, this number is also called the natural base. The function given by f of x equal to e of x is also called the natural exponential function, and its graph is shown here. So you can see this also mocks what we were talking about with a to the x. This time our a being 2.7182818828, and goes on and on and on. And this is why we use this button E. You will not punch this in, you will always use the E button. So be sure that for the exponential function, f of x equal to e of x, e is the constant, whereas x is the variable. So don't get confused in the fact that e is a letter, because only x is the variable. E is like pi. It's a symbol that we use to dictate a value that we know, and is unroundable. It's roundable, but it's not exact. So I want you to become familiar with your calculator. So evaluate the functions for these values. And again, you're using f of x equal to e of the x. So in this case, I want e to the -2. Okay, so when you go to type that in, you're going to say e, and normally that button is under an ln button, so see where it's located at. Most of your scientific calculators, if you're using one that's not been just overly used, it has a little paper in the slide of it. Use that if you need to figure out these keystrokes. And then you're going to raise it to an exponent, and then it'll open a parentheses and a -2. Now, this is how mine works. Yours may work in the fact of you need to hit -2 and then your E button. So play with it and then make sure your values are matching my values. This is important as we go on to like solve things out. You don't want a calculator error to mess you up. So let's go on and see what these answers kind of look like. So f of negative 2, e to the negative 2. Remember, my keystrokes is e, and I have to do my housetop and then a negative 2. And mine actually types all that in. Yours may be the reverse of that. So play around with it or find that little sheet of paper that's in the slide part of your cover. Important thing is make sure that you're able to get 0.135. If you need to, pause the video now, play with it until you get this answer. E to the negative 1. Again, I got 0.3678. And if I went to round that, that'd be, let's see, 0.368. E to the 0.25 would be 1.284. And e to the negative 0.03, that would be 0.741. So again, pause if you need to. Make sure you're able to type all these in. Everyone's calculator is different, so make sure you use a scientific calculator. Simple will not work. If you're grabbing your phone calculator, be aware you will not be able to use your phone calculator on this exam. So it does not benefit you to use that one as you're practicing typing this in. So let's look at some applications of these evaluations and these exponential functions that we're just starting to get into. One of the most familiar examples of exponential growth is an investment earning continuously compounded interest. To accommodate more frequent quarterly, monthly, or daily compounding of interest, let n be the number of compoundings per year and let t be the number of years. Then the rate per compounding is r over n, and the account balance after t years is the following. So I would write this down. This is our compound interest formula. Compound interest. So if you let the number of compoundings n increase without bound, the process approaches what is called continuous compounding. And we'll have another equation for that. So here's a nice blue box from your book. It says after t years, remember t is always in years, crucial information there. The balance A in an account with principal. Principal is how much you are borrowing or investing. And annual interest R in decimal form is given by the following. So again, A, I'll write it in more handwriting you can actually read. Okay, so let's see, we're looking at the account balance. P is your principal. And again, that's how much you invest or borrow. Like if you want to borrow $10,000 to buy a car, P would be how much you're wanting to borrow, which is $10,000. Your annual interest rate, that is your percentage of your interest rate, and you always want that in decimal form. And then T is always in years. That's your time, always in years. So if they give you a month, make sure you put it in years. Let's see, we got A, P, R. And then N is how many times you're compounding. So if it's like, if you're talking about annually, that'd be 1. Semi-annually would be 2. Quarterly would be 4. Monthly would be 12. Daily, they'll instruct you, there's 365 days. But a lot of times they might use 360, and they'll tell you that within the problem. So these are some examples of ends that you might see. They're not just give it to you as a number. They're going to have you interpret those words. And so in your notes, make sure you understand these two equations, and you will have to memorize them. No formulas will be given. And you can see in the compounding continuously, P is the same thing. It's still your principal. E is the natural base E, and then RT is still your rate and time. Okay, so it has less variables, but they do mean the same as you encounter them. So here's a problem. A total of $12,000 is invested at an annual interest rate of 9%. Find the balance after 5 years if it's compounded quarterly, monthly, continuously. So first, let's write down the information that we know. First of all, we have a total of $12,000 that's being invested. So P is equal to $12,000 at an annual interest rate of 9%. So R is equal to 9%, but we always use the decimal, so 0.09. Find the balance after 5 years. So my T is 5, and that's in years, so we're good. When it's quarterly, we're going to say n is equal to 4. When it's monthly, that's n equal to 12. And when it's continuously, we're going to use a different equation. So the first equation you would want to use is A equals P 1 plus R over N to the NT. And I'm just going to look at part A. And we're going to go through these. But if you think you have an idea what you're doing, you can pause, work it out, and then come back to it. So I'm going to know the amount I have. I'm going to plug in 12,000 for my P. 1 plus 0.09 over 4 raised to the 4 times 5. Now when you go to enter this into your calculator, go slow, and I would write down what I'm doing so that if you enter it incorrectly, you have something to fall back on or possibly partial credit. So 4 times 5, I would go ahead and multiply that to be 20. I would do as much simple arithmetic as I could before I went to my calculator and just type it all in. I would go ahead and do 0.09 over 4 and then add that to 1 and put 1 point, whatever you get for that decimal, and then go to your calculator. And you're going to enter first the base raised to the 20th and then multiply by 12,000. So let's see what that looks like. So here it is. For quarterly compounding, we have n to equal 4. So in 5 years, the balance is, you can see we wrote our formula, we plugged it in, and then like I said, go ahead and multiply this together to give you 20. Go ahead and divide this number, 0.09 divided by 4, and then add that to 1. Raise that value to the 20th power, and then multiply by the 12,000 last. So if you use your calculator, you should get 18,726.11. Because we're talking about money, we always round to 2 decimal places. That will be points off. If you do not round to 2 decimal places, it will not tell you that. You are to know that when you're working with money, you round to 2 decimal places. If you're not getting that value right now on your calculator, stop the video, try it again. Make sure you're able to get this value now. Same thing if you're wanting to find monthly compounding, except our n is going to turn to 12. It is the same equation, except now I'm plugging in 12 here and here. So again, do your arithmetic before you start kind of going through all this. This would give me 60, and then you want to divide the 0.09 by 12, add it to 1. Take this value, 1 point whatever, and raise it to the 60th power. Then multiply by 12,000. Again, you should get 18,788.17. Do not round until you get to your very last answer. And the last one, because we're talking about it's compounding continuously, you have to use a new equation. You have to use A equals PE to the RT. PERT for short. Your P is still the same. It's still 12,000. E is that button we talked about earlier on your calculator, and 0.09 to the 5th. So again, I would find this value first. Then raise E to that value. Then multiply by 12,000. Go in that order. And that's, please excuse my dear Aunt Sally, order of operation. You do your parentheses first, which would be this up here. Then your exponents. That's this circle here. And then you multiply or divide. So that's that multiplying by 12,000. Again, use your calculator, 18,819.75. So I hope this helps with your first section. You will have to know those 2 formulas and how to use them. And you can see you will have to have a calculator for this exam. A scientific calculator. Graphing calculators will not be allowed on the exam.